Welcome to The Explainer. Today we are cracking a fascinating code. We're going to tackle a really monumental challenge. How in the world do you teach a machine to actually understand human language?
I mean, think about it. It's a massive challenge, right? At its heart, this is the central question of what we call natural language processing, or NLP. It's all about translating our complex, kind of messy, and beautiful world of words into the cold, hard logic of ones and zeros that a computer can understand. So, let's dive into this. We're going to see exactly how machines climb this ladder of understanding, really one step at a time. Okay, so we're going to start way up high at the 10,000-foot view. This is the first, and you could say the most basic form of comprehension, just figuring out what a piece of text is generally about. You know, getting the gist.
And you actually see this in action every single day. You know when an email automatically gets flagged as junk? Yep, that's text classification. Or when you're looking at a product review and it's summarized with a star rating, that's text classification too. It's honestly one of the most common and practical uses of NLP out there.
What's really fascinating here is the evolution of the tech. We started with a pretty simple bag of words approach. It's literally like throwing all the words from a sentence into a bucket and just guessing the topic based on what's inside. It completely ignores grammar and word order. Then we moved on to models that could read a sentence forwards and then backwards to get more context. But now, state-of-the-art transformers can weigh the importance of every single word in relation to every other word. This lets them capture context in a way that was just, not possible before.
All right, so once a machine kind of gets the main idea, it needs to zoom in. It has to start identifying the individual components. So what are the fundamental building blocks of this sentence?
This is basically the machine's grammar lesson. Is this word a thing, an action, a description? It's an absolutely critical step because understanding these roles is the foundation for pretty much every other complex language task that comes next.
And what's so powerful about this is the effort to standardize the whole process. Thanks to amazing projects like universal dependencies, we now have a consistent set of tags that can apply across dozens of different languages. It's kind of like creating a linguistic Rosetta Stone, but for machines. So, if part of speech tagging is all about grammar, then named entity recognition, or NER, is about finding the main characters and the settings in the story. You can think of it as the machine taking out a digital highlighter and just marking up all the proper nouns in the text.
But here's the thing, this is not easy, not at all. Look at this sentence. The same word, Washington, can mean completely different things. Is it a person? Is it the government? A city? Context is absolutely everything. And this is where these models really have to prove they understand more than just vocabulary.
So how does a machine know that Jane Smith is one name, not two separate words? Well, it uses a clever little tagging system. A simple one called BIO marks the beginning of a name, which would be Jane, and what's inside it, like Smith. But there are even more precise systems like BILU, which can also mark the last word of a name, or even tag a name that's just a single unit word like John. It's a simple but really crucial system for telling the model exactly where a name begins and where it ends. Okay, so let's recap. The machine has the topic, and it's identified the key parts. Now for the truly complex step, figuring out how all those parts connect to each other to actually create meaning. This process is called dependency parsing, and it's kind of like creating a grammatical family tree for the sentence. It finds the main verb, that's the root, and then it maps out every other word's relationship to it. It's how the machine finally understands who did what to whom.
But this can get really tricky. A simple model might accidentally create an impossible loop. Like, it might say the word dog modifies the word big, and big modifies dog. It just doesn't make any sense, right? So to solve this, the algorithm first maps out all the possible connections. Then, it uses a really clever method to find the single most likely structure that forms a coherent tree, one with no illogical loops.
So after all that work, the classification, the tagging, the parsing, what can a machine actually do with all this? Well, this foundation enables some of the most sophisticated and genuinely useful NLP applications that we have today. Let's take question answering. There are two main flavors. The first is extractive QA, where it finds the answer by literally highlighting a span of text from a document, kind of like a scavenger hunt. The other is multiple choice QA, which is more like a school exam where it has to choose the best option from a list.
And
And what's so clever about this extractive method is that the model doesn't even write new text. It just learns to predict two things: where the answer starts and where it ends. And what if a question is unanswerable? The model is trained to point both its start and end markers to the very beginning of the passage, which basically means, sorry, the answer just isn't here. It's so simple, but so effective.
And this leads us to a huge breakthrough in the field: unified models. Just look at the elegant idea behind models like T5. Instead of building a totally separate AI for every single task, researchers trained one massive model on 18 different language problems at the same time. The genius here is that every single task is framed as a simple text-to-text problem. By just changing the prefix from translate to summarize, the exact same model can switch from being a translator to a summarizer just like that, on the fly.
So there we have it. We've completed our journey. We've seen how a machine starts with that blurry 10,000-foot view, then zooms in to label all the parts, maps out the connections between them, and finally uses that deep structural understanding to perform these incredible feats of language.
This constant evolution, from these simple building blocks to these unified, multi-talented models, is exactly what makes the field of natural language processing so dynamic and exciting. It really pushes us to wonder, what comes next? And how is our relationship with technology going to change when machines don't just compute, but truly begin to comprehend?